I couldn't resist talking a little bit about deep learning. Although I haven't worked in deep learning in the way it is perceived and understood nowadays, I thought I would talk a little bit about deep learning to try to see what you think of it and what deep learning really is. By the way, I'm assuming that at least some of you would have heard of deep learning, deep neural network, and the work that Jeff Hinton has done recently, which is clearly very, very good. But here it is. So Jeff Hinton and Alexander Krzyzewski and Sutskever came up with a neural network structure for image level classification. So given an image, like a picture of a bear, it tells you what that is. It comes up with a label for the entire image. So this has nothing to do with segmentation. This is image level classification. It is a classification engine. It is supervised classification, and it's done via neural network. Now, the thing that makes this system interesting is, first of all, that it works incredibly well, much better than predecessors. And the authors claim that the reason why it works so well is because of the deep part. Deep means that the system is made of layers. So you have the first layer here, second layer, here, third layer, fourth layer, fifth layer, and then the last layers are a bit different from all the others. So each of these layers, what they do is they convolve the previous input with some kernel or with a set of many kernels. And so they produce a filter response, which in this case is made out of 96 responses. So 96 kernels have been applied at the first level. And also there is some sort of subsampling going on at the same time of the original image, so as to reduce it down from 227 to 55 by 55. And so on. And then there are some nonlinear processes as well, like it's called max pooling, and then the whole process is repeated again. So they do convolutions of convolutions plus nonlinearities, this blue kernel. Then convolution of convolution of convolution plus, or in this case, they decide to remove the nonlinearity and so on. So it's a very interesting, very well designed and quite complex system with a lot of parameters. In fact, there are 60 million parameters. Which clearly works very well in the ImageNet challenge. But this is not completely new. Well, neural networks are not new, and the fact of using a deep architecture, which effectively means using the output of some preliminary process data as input to new process, this idea is not new either because it is called stacking. So in machine learning, the idea has been around for quite a while, at least since 1992. It's called stacking by Wolpert. And so stacking is, is what we just said. So you have your training data set. Remember my representation with the squares representing features and then some classes attached to them. So you extract some sort of feature representation out of them. We call them features 0. And you learn a model, a classifier model, okay? And let's imagine that this classifier, rather than spitting out labels directly, it spits out a new representation, new features, which are processed, through nonlinear processing, and it is learned. So whatever happens in here, the parameters which get stored into this model are not just hand-designed, they've been tuned looking at a well-defined energy function, training energy function, and some well-defining data set. And then you repeat this process. And now, in order to train the level 1 model, then you can use the features 1 as output, the output of the model 0 as features, as input to this, in conjunction with the features, the raw features that we use at the beginning, and so on. So this is called stacking, and nowadays it gets renamed as deep learning, but that's what it is. But what I'm trying to say here is that deep learning is, or stacking, is not a synonym of neural networks. And the classifier that you learn in each of these intermediate steps can be anything that you like. Okay, it could be an SVM, could be a forest, could be something that you feel comfortable with and works for you. Another way of interpreting deep learning is by saying, this is, by the way, my definition. It's not something that has been vetted by the NIPS community. So, I might be wrong, and I often am wrong, but that's more fun. So, another way of thinking about deep learning is also as representation learning. This is another buzzword that goes around. And it really has to do with what we said, with the fact that the data is transformed in stages. We go from raw features, from some features which are output of some sort of classification stage. So you can interpret them already as being a little bit more semantically rich, a little bit more label-like, but at the same time not quite. They're still quite close to the raw features. And then more and more and more and more. So you can see as a line where you go from completely raw features, could be the RGB pixels of your image, to something which is intermediate, mixed, to something which is my desired final fully semantic output. So this is an interesting way of looking at this. So the three things perhaps that define deep learning is definitely the stacking bit, the fact that you have higher order functions, you have functions of functions, could be convolutions of convolutions. You have this representation learning where the data, intermediate data, is transformed one stage at a time from completely raw features to semantically rich outputs. And also, it seems to be quite important to have this other ingredient, which is non-linearities, non-linear transformations, not necessarily all the way for each stage, but at least in some of them. But the important thing is, at least from my point of view, is that this is not necessarily a synonym of neural network. And we can learn from what has been done by Hinton, LeCun, and Fergus, and many others, and many other fantastic pieces of work, in the realm of neural networks, and see what happens when we plug in a different type of classifier. And that is also not new. So, for instance, we have the work of Zhuwen Tu, who used to work at Siemens with Doreen Comeniciu, who invented the probabilistic boosting trees, which are used quite often at Siemens and elsewhere. But also he came up with the idea that he calls auto-context, which is nothing else but stacking, once again. So in here you have a training data set, and each of these, imagine being a single tree, but it might as well be an entire forest. It might as well be an entire decision forest. So this is another way of doing deep learning with forests. But then, when we were thinking about this whole structure, I also thought, wait a minute, a tree has got the peculiar characteristic that it is a set of trees. It's a hierarchical definition. It's a recursive definition. So what we can do is we can do stacking this other way. So I can think of, imagine training a single tree. I can train a section of this tree, breadth first, for instance. I call this section 0, and I stop here. This in itself is a very well-defined, self-contained tree. Right? I can already test that tree. I can already extract some probabilities of my classes as output. And now I can do the stacking. I can use the output intermediate probabilities, which are not particularly well refined. They're not fantastic if I want to use them as probabilities directly, but already contain some semantic information. I can use them as input into the next layer, into the next section, in conjunction with the original features. There should be another arrow here going straight from the original features to section 1. And this is something that neural networks don't necessarily do. They can do it, but I haven't seen it done. Always making sure that you always plug in also the raw features in such way as to avoid mistakes being propagated, right? And so at each section, I can train a decision tree section by section. In each section, I can have, I don't know, 5 layers or something like that, 5 levels, I should call them. And each section is trained using as input the output of the previous level, which in this case is a multinomial distribution in the case of classification, as well as the original features. And then at each section, the section decides to use a combination of those probabilities and a combination of the raw features. And what we, again, one of the beauties of decision trees is their interpretability. So once you have trained a tree in such a way, which by the way we call them entangled trees, just to come up with a new name, what you observe is that as the tree gets deeper and deeper, each section tends to use more and more the previous probabilities rather than the original raw features. While at the beginning, of course, you only have the raw features to work with. So it is a form of transformation of the features into semantic labels. It is representation learning. It is, in my opinion, deep learning. And if you don't agree with this definition, come and talk to a Sicilian. Now, we have used this form of deep learning based on forests for semantic segmentation. And we have used it and applied it to a large number of different data sets of different types of images. Now, when you do semantic segmentation, you want to have certain criteria in mind. You want it to work well. And what does that mean? You want to have segments which are compact. You don't want to have scattered pixels. And this has been the realm for decades. Has been the realm of Markov random fields, conditional random fields, and all sorts of similar techniques to help impose this compactness of the representation. You also want to be able to segment nicely long and thin structures, like in this scene there could be the lampposts, or in a medical setting could be thin blood vessels or brain fibers. But also, I personally care a lot about the use of semantic context. And here I use the word semantic with a very specific semantic. Gosh, I got entangled there. I will tell you a little bit more about what I exactly mean with that in a few slides. Just like you see here, our semantic segmentation approach has been applied to medical images, to street views. These are images from Cambridge, the real place, not the other place, and as well as Kinect data, depth images. So a little bit of background. Many of you are familiar with semantic segmentation. For the ones of you who are not, this is the sort of stuff we want to do. We want to, for each pixel in an image, we want to not only color-code it, not only group the pixels into compact regions which have got uniform or similar colors. That's not particularly useful, I don't think. But we want to group them together based on their semantic. So for instance, you want to be able to say that this is the right eyebrow, this is the left eyebrow, the eye here, the nose, the bottom part of the face, the mouth, and so on. And we do this, we can do this by using, right, so, and then if I use my definition of semantic segmentation is that of attaching a single class label to each pixel. So it is a classification problem which is applied to every single pixel. So you can solve it using machine learning, you can solve it using a classifier. But inevitably what happens is that if you use a single classifier and apply to individual pixels independently, you end up with a lot of noise. So it's not very clear here, but there is a lot of light green and pink scattered all over the place. So just like we said before, we want to impose spatial compactness. And just like I mentioned, this has been done in the past many, many times with many different models which have been evolving over the time. So we started with Markov random fields, for instance, where people were using 4 neighbors, then 8 neighbors, then you started to look at much more complex structures and higher order terms, and in particular, Pushmit-Coley and Lubor-Ladicki at Oxford did a lot of work in this area. And these models are very nice from a mathematical point of view, but they're not particularly efficient. When you need to do the inference, you really come up with the best marginal probability estimates for the pixels which are under this sort of complex models. The machinery is quite complex and the algorithms can be quite long-winded. So the question is, okay, let's go back to forests. We like them because of their simplicity. Can we enable forests, with some changes, some modifications, to take care of spatial compactness and spatial continuity, as well as good classification? Can we do everything in one go within one algorithm, rather than doing a pixel-wise classification and then a mark random field type post-processing or inference of the graph? So that's the question that we asked ourselves, and so we worked hard to do this, and we came up with a paper that was called Entangled Geodesic Forest, and was presented at the last CVPR by my student Peter Consider. Fantastic guy, really, really good. And there are two ingredients in this piece of work. One is the fact that we use some new type of features which encapsulate and model connectivity between two pixels, even very, very far away, even at the long range connectivity. And also there is a new training regime and a new surrogate training function that we minimize. So let's talk about these two elements one by one. So like I said, in the case of Kinect, we have depth images, and from these we classify each pixel with 1 out of 31 body parts. We get this sort of image. Great. And like I said earlier, there is a lot of noise here. The pixels are not particularly compact together. The clusters are not particularly compact and together. This is also a low resolution image. And this is because with the very low computational budget that we have for running all this operation on the Xbox 360, which is an old machine, we couldn't afford to do a lot more. But also, the type of features that are used are very, very simple. So imagine that this is my depth image, and this point I in yellow is my reference point, which I want to classify as belonging to the shoulder, the head, or the knees, and so on. What I do is, within the forest architecture, at each split node, during training, I try out many, many possible features, and by feature I intend this pair. Looking at a probe pixel, this I prime probe pixel in this position, this far away to the left, and I read out the depth at this pixel, and I compare it with the depth at the reference. So just a simple subtraction. And as you can see, the value of this difference might be roughly the same here and here, but it will be wildly different if I move this pair together inside the body. And if I use this other pair, this other feature, then I will get different results if I apply here or if I apply here. And so you can see how by this very simplistic, easy to compute features, I can get some information about where I am in the body. And if you have a very, very large combination of these features organized in this hierarchical tree-like structure, there we go, bam, we have our classifier. That's how it works. However, if we apply this to medical images, perhaps we can do a little bit better. We can use a little bit more clever features. Imagine, for instance, let's just look at this pair of pixels in green, P1 and Q1. This is a CT scan. So both P1 and Q1 land in regions of prevalently air. They are inside the lungs. Now, if you just look at the intensity underneath P1 and underneath Q1, they are both very close to 0 in Hounsfield units, and 0? No, whatever it is, negative, yes. And so air, because there is no density whatsoever there. So the difference is 0. So just by looking at that, this will give us a little bit of information which says they probably belong to the same class, probably belong to the same lung, which is clearly not true, because there is a big gradient, a big mountain to be crossed if we really want to join the 2 points. So perhaps something a little bit more interesting would be not only to look at the beginning and the end, but also to look at whatever happens in between. So you can imagine, for instance, running a shortest path sort of algorithm for every single possible pair of voxels in my CT scan. right? So it is clear that running this algorithm would provide features which would be a lot more informative, but it is also clear that that is going to kill us. I mean, it's going to be computationally really infeasible, despite the fact that there are modern algorithms for shortest path computations, Dijkstra-like algorithms, which are very efficient, but you have to do this computation for every possible pair of pixels or voxels in the image, both at training time and, more importantly, at test time. You can't avoid it. And that's the reason why these sort of connectivity features are not difficult to invent, but are very difficult to implement. And people haven't used them because they are intractable. So what can we do? Well, we're lucky because a few years ago we had a SIGGRAPH paper where we were talking about something called generalized geodesic distances. So normally, given an image and given a binary mask, which has got 0 for where the object is, by whatever definition of object, and 1 everywhere else, you can use the gradients of the image to compute all possible distances from every point in the image to the object. But that is if you have a binary mask. What we did was transformed very slightly the maps of geodesic distance transforms to be able to deal with soft masks, masks which not only have 0 or 1, but also have grayscale values. And this is very important because now this could be some sort of probability. It could be a likelihood ratio. It could be a measurement, an image which is the probabilistic output of a classifier. We don't need to threshold it because threshold it would kill it, would remove a lot of really useful information, but we can use it as it is. And really, rather than having 0 or 1, we have the entire range 0, 1, which indicates some sort of belief of belonging to the object, in this case a flower, or the background. Don't worry about the equations, the maths is actually quite simple and very easy to implement. But how do we use it? Imagine that we are in the Kinect world and we're talking about the Kinect-like type of application. So what we want to do is we want to recognize a human body and assign 31 classes to all of the pixels. Imagine that we stop short and we only visualize the probability that we get for the class torso. Here, this is a much smaller subset of body parts, only 8 or so. So this is a very rough, inaccurate probability that we get from a classifier for the torso. Excuse me, and this is the same for the left leg. So using these maps and this transform, the geodesic distance transform, generalized geodesic distance transform, we can obtain these other images. So again, difficult to see, but these are much smoother versions of these probabilities, which are also diffused a very long way into the arms, for instance, into the head, or here the left leg class diffuses into the other leg. So, and also the other important thing is that edges, strong edges, are very well respected. So this sort of physical diffusion process is like water diffusing on a surface or paint, stops when there are big, strong barriers, which are represented by the edges, the gradient in my image. Okay, how does this help us with the problem that we had, of computational inefficiency? Well, imagine that in our Kinect problem, we do this for all the classes. So imagine that these are the 31 body parts. We can do this sort of geodesic smoothing operation, if you want. It's very similar to bilateral filtering operations as well for all the classes. Now what you can do is we can use these spatially smoothed, spatially and gradient-aware smoothed versions of probabilities as input to the next classifier in a stacked way. So let's go back to medical images and let's apply this step by step. So we have a CT scan and I want to be able to segment the heart from the lungs, from the rib cage and so on. So I start training this tree using completely raw features and using, if this is my reference point, I can look around at raw features, raw CT intensities. I can look at the intensity underneath this point P1, P2, P3, P4. No shortest pass here whatsoever. Everything is super efficient. And what I do is I stop after a certain number of levels. I'm done with training section 0. But if I'm done with training section 0, it means I can already test that tree on that image. And therefore, for each of these points, I can assign a probability, a soft probability for each of the classes of interest. Imagine that my classes of interest are left lung, heart, and right lung. So I can also, there we go. I can also geodesically transform these probabilities, the posterior for the right lung and the posterior for the left lung. And this blue overlay and this green overlay are precisely these transformations. Now, if I've got my reference point here in the heart, underneath the probe position P1, I can read both the original intensity, the original raw CT intensity, as well as the value of the probability for it being the right lung. Again, that probability normally is not as beautiful as this. It's very messy, very noisy, not particularly well refined. I can do the same for P2. And so after section 0, I already start to gather some not particularly convincing, but perhaps already informative in some cases, information about the context, the semantic context that surrounds me. The reason why this is semantic context is because it is really related to the classes that interest me. The probability is a posterior probability over the class right lung, the posterior probability of the class left lung. And this diffusion process takes care of the spatial smoothing at the same time. And so then I can proceed and I can train different sections of this entangled tree using every time more and more refined versions of my geodesically transformed posterior probabilities. And so what I obtained is this cascade, again, this representation learning effect, where I start from completely raw CT intensities and I get, roughly, not particularly well-refined class probabilities, then a little bit more refined, until at the end, I get the most refined class probabilities I can get with this model. Does this make sense? Yay. And of course, I can move on and have multiple trees, and as usual, having an ensemble on top of whatever classifier you like, it always helps. Inevitably, it helps. Right. So the other thing is, okay, what do we do in terms of training? Earlier on, someone was asking me about, dealing with, imbalanced classes, different number of classes. And we have studied that problem as well, which is actually also related to spatial smoothing and all that sort of stuff. Unfortunately, again, the image is not particularly clear, but what we try to show here is that if we use just entangled trees with geodesic transformations, we get decent results, but we get even better results if we change the energy function that we minimize during training a little bit. Rather than using straightforward information gain, we use something, an information gain like energy function, which has also been informed by the imbalance of the original classes. Okay, so if I have, normally in segmentation problems, I have way more background than foreground classes in terms of training. So you need to either rebalance the number of pixels you have at the origin by subsampling, for instance, or reweight the contribution of each of the training examples based on the inverse frequencies. Effectively, I'm not going to go into the details of the maths here too much, although it's very simple algebraic derivations. But what we show in this paper is, first of all, that under certain well-defined conditions, using the standard Shannon-like entropy and the derived information gain for classification is absolutely, completely identical to the standard unary term which is used in GraphCut. It's exactly the same thing, but assuming a big assumption, which is that you don't have any spatial dependencies in the neighborhood. But this is already something new and interesting, which led us then to transform. So this is the equivalence. which led us to transform the derivation for the information gain using this field-inspired energy. And effectively, the difference between the Shannon information gain and our new formulation of information gain is just a factor that comes out from the sum. And it is, a general, and it doesn't depend on, it does depend on the split node at which you arrive. It's a very small change in mathematical terms, but it is derived from standard algebraic computations, and it wasn't shown before, and it shows the connection with MRFs, which is quite interesting. So I'm moving quite quickly to experiments and results so that we will have more time for questions at the end. So we tried this approach for semantic segmentation on 12 different data sets. So these are just some of them. So the faces, computed tomography, Kinect images, and unlike the excuse me, Kinect images were, unlike the original Kinect data set, here there is also background. So these people are shot, in their environment where there is sofas, lampshades, curtains, and all sorts of things. And so the classes that we're interested in is not only the different body parts, but also what is in the background. So is it the ground floor? Is it the back wall? Is it furniture type of thing? So it's slightly different, and as you can imagine, a little bit more difficult. Then there is Roberto's data set of driving scenes in Cambridge, and then there is Dario Gavrila set. These are stereo images for Mercedes, for Daimler, in fact. And we have many more. We have the Kitty database from Raquel Hurtasun and many others. So just to give you some examples, some qualitative results first. So what you see here, the original image, the image in this case is in these images is already cropped. It comes this way in the dataset. Gosh, I spilled my water. What you see is, again, here the effect of different tree depths. I can't remember how many trees we use, but it's in the dozens. And you see, with a relatively shallow tree of depth 15, you get most of the regions and the location all right, but they all look like bushy, sort of very hairy people with big noses. As you increase the depth of the tree, things get refined nicely, and you converge to a much nicer behavior. By the way, at this point I should say that don't extrapolate from this, because if you use depth 30, you might overfit. And so depth 30 might work a lot worse than depth 20. So there is a sweet spot that you have to find, and it depends on the application. So this is another slide which shows some sort of robustness with respect to pose and illumination changes, some occlusion, and also the presence of multiple faces. And here you think, well, wait a minute, something is going wrong here. Why does it detect only one face when there are 3 faces? Well, in this data set, because most of the faces are single faces in the center of the picture, effectively, the forest has learned a very strong prior for the fact that there has to be only one face in the center of the picture. And so it discards all these other faces. Again, this is something that you might want, might be a desired thing, or might not. It depends on, so you have to be careful with these things. Also, in this case, the mustache and the tennis ball in front of the people's faces disappear from the detection, and the forest is capable of reconstructing behind those objects. Once again, there seems to be some strong prior that gets learned automatically by the system, by the geodesic forest. Now, in some cases, you might not want that, so you need to be very careful with this. I think I've got water, thanks. So this is on the Kinect plus background data set. So we have lots and lots of these input images. They're all labeled, and here's the ground truth. Again, a subset of the body parts, but then we have other regions in the background, like the floor, the back wall, and then everything else, which comprises furniture and all sorts of other bits and pieces. Once again, you see that at depth 15, the segmentation is not particularly good. It's roughly okay, but this small guy here has got huge boots. which get refined as you go along with deeper trees. Now, this is the CAMVID dataset, where the classes of interest are things like cyclists, the tree, the sky, buildings, the road, surface, and the pavement, and fences, and other things like this. Once again, it's difficult to see here, but we tend to do better and better as we move on, especially with very thin structures, though it is still difficult to do fantastically well there. This is, again, I'm going through a lot of examples because what I want the take-home message to be is that these are general algorithms which were not designed just to work on medical images, but also to work on medical images. Now, when I started working in medical images, one of the major criticisms I got was, oh, but your algorithms are way too generic, and if you want to be successful in medical imaging, you have to really know the medicine and really know the nitty-gritty of how the left ventricle of the heart works and its shapes and so on and so forth. I'm fighting that, and I believe that a lot of progress can be made the other way around, with understanding the generic algorithms, the generic principles which we know work in the biggest amount of data sets and images, and then if I need to spatialize it to work particularly well on the left ventricle, I will do so. But it's almost like a small processing box that you attach on top of something that works already. So that's my way of thinking about things, or perhaps my way of justifying my lack of knowledge in medicine. So in the Dario Gavrilla dataset, we do particularly well, much better than state-of-the-art. And thinking of that, perhaps we should move on. Oh, there is still medical imaging. Oh, this is interesting. So here we have a lot of CT scans. This is a 2D illustration, but all the work is done this is a subset of 2D images, 2D slices taken from 3D volumes. And the reason why I did this is because I wanted to try out an idea. So depending on where you take the coronal slice, that cuts across the lungs, you might either intersect the spine, like in this case, or you might intersect the heart, or maybe you intersect the aorta only. Okay? So in this case, you see a little bit of aorta attached to the spine. In this case, you see the spine only. In this case, you see the heart. It depends, how deep you go, right? Now, in these images, these are the ground truth segmentations. Because our system is using semantic context, I was really curious to see what would do with things like the aorta, which normally sits, in healthy individuals, in between the lungs. Now, in this case, you see that at depth 15, despite the fact that the aorta was not there, because we have, big lungs, the system says, oh, this is all orange. I'm hallucinating the aorta there, and this is a mistake. The system at this depth is relying way too much on semantic context. But remember also that in our entangled forest, in our way of doing deep learning, we always reuse as input also the raw features, not just the output of the previous classifier, which in this case goes wrong. So in the next level, or next two levels, level 17, you see that the system realizes that actually the appearance doesn't quite correspond to the context. And so it starts to remove the aorta back away from the labeling that it gets. And so it corrects itself. This is great. I think, to my knowledge, this is the first time I see a context, a system which is capable of modeling and capturing semantic context, but is also able to remove it when it's actually hindering you rather than helping you. In this case, it does the same thing. So it starts off with everything being aorta, and then it removes it until it keeps just the region where the aorta truly is. And similar here. So this is a good result. We can go on and look at cross correlations. For instance, let's try to understand really what this context is doing. So if we condition ourselves to have the reference point in the left kidney, in medical imaging, as you know, left and right are inverted because this is seen from this way. So in the left kidney, we have R, the reference point. In which regions are my, if I use 2 probes at every split function, in which region are the 2 probe points more likely to be? So you see that at depth 11, they are likely to be either on the right kidney or on the spleen. That's interesting because the spleen in the right kidney, left kidney, sorry, left kidney, here is where it's higher, and spleen. So the spleen and the left kidney are very close to one another. So again, this shows the fact that the system learns to use contextual information. If, for whatever reason, the spleen in that image happens to be very well delineated and easy to segment, then the system uses that just a little bit like we showed earlier on as an anchor point or an anchor region, a landmark region, to vote for where the left kidney is. If we go to depth 14, this cross-correlation matrix changes and it uses things in a more symmetrical way and so on. You can analyze how the context is used and to what level it is used. In terms of numbers, so these are, here we have all the 12 data sets. These are just coding for faces, Kitty, the CT scans. No, sorry, this is Kinect, this is Kitty, this is the San Francisco, New York, CamVid, and Daimler datasets, different versions. And what we do is we report both the Jacquard index, which is the intersection of our union, as well as the pixel-wise accuracy. Now, the Pascal challenge people have fought hard to introduce intersection of a union measurement, and that's a great thing. It's a very good measure to use because with the pixel-wise accuracy measures, it's way too easy to get over 90%. And so then you go like, ooh, I'm 98.2%, which is better than 98.1%, and that gets a little bit ridiculous. The Jacquard index, or the intersection of a union, is also called the Jacquard index in medical community. It's much more sensitive, much harder to get to the 90%. And so differences in these numbers are somewhat more representative. So I normally tend to look at the green column more than the blue column. You can see that in all cases, when we use geodesic forests, which is all the stuff that we talked about, and compare it with either standard pixel-wise decision forest or with a decision forest followed by a condition random fields whose parameters have been optimized on each data set individually, we always win. In some cases by only 1 or 2%, in some other cases by a larger margin. And in Jacquard terms, 1 or 2% is, corresponds to a big visual difference. So this just shows that it is possible to use decision forests with small modifications to do spatially consistent semantic segmentation without the use of a second stage post-processing based on a graph-based optimization technique. In the case of deep learning entanglement, you also need to be careful how many sections of entanglement you use. Just like in neural networks, if you use too many, you risk overfitting, and that's why you have this sort of sweet spot somewhere. It happens at a different section level for different data sets because it all depends on how complex the data sets are. But also, things change on a class-by-class basis. And so, for instance, here we have, let's see, this is the face data set. And here we have, the background class and the face class and the, hair class. In yellow, we have the geodesic forest, and in red is the standard forest followed by a condition random field. What you see is that in most cases, the yellow bar is higher than all the other bars. And this is especially true for the classes like hair, or eyebrows and eyes here, which are particularly difficult to segment. So, thank you. So, it looks like the geodesic forest approach really helps, where it is most needed for the most difficult classes, which are normally either the ones which are smaller, and therefore for which we have fewer training pixels, training examples, or they are, long, elongated, and thin. So it's going in the right direction, and it's definitely a good alternative algorithm to the more common conditional random field type algorithms. Now, I'm almost finished. We're all tired, but here is a little bit of fun, even more fun, if that is ever possible. So there is a new application we're thinking of, which is called Depth for Free. And it's also going to be, a version of this is going to be a SIGGRAPH paper. So we're very proud of that. And so it's a very simple idea. We have Kinect, which is a fantastic depth sensing device. It's not the only one. And it's one of the best, but not the only one. But we also have tons and tons and tons of standard monocular cameras, like the one I've got in my laptop. Can we ever mimic depth sensing with a non-depth sensing device? Can we train a monocular camera to behave like a depth sensing camera? And so, that's an exciting idea, which if it works, will put out of work many of my colleagues, which is not great, but still interesting to try. So what we did was we took a standard Xbox Kinect, which comes with a standard RGB color camera as well as a depth camera, and the two are roughly registered and aligned together, or they can be made that way. And so for the specific application of Skype chatting, video chatting, we trained a system which, given pairs of RGB images of talking people and the associated depths, can actually make the associations and from an RGB image only reconstruct the depth or predict the depth. And even if you move far or close to the camera, or if you wave your hands, or if you have an object in your hands, it still works. It's not just, it doesn't just work for a head on top of shoulders. If you move your hands, it does a reasonable job. And that's the testing phase, where indeed we replace the RGB with a completely common standard off-the-shelf cheap monocular camera. And for the specific scenario, I repeat this over and over again, for which we train the system, it works very well. But of course, if you take the system outdoors in an area where it hadn't been trained before, it gives you rubbish. And these are just some comparisons between the ground truth. These are quantized depths. For laziness, I used a classification approach rather than a regression approach, but it should work with regression too. And these are the estimated results. These are all test sequences. And it's always me here, but now we have something like 200,000 video sequences with many, many different people in many different environments, all to tackle this sort of video chat application. And there is a modification of this which uses also an IR, a very cheap infrared-based active illuminant. And that's what will be presented at SIGGRAPH. Now, as a summary, I philosophized a little bit about what deep learning is. I think we need to do a little bit of that to really understand what that is and the great potentials that I think it has. And I try to bring home the point that deep learning is not a synonym of neural networks, is not a completely new invention, and can be done by all of us with whatever classifier we have. It seems to work particularly well when combined with neural networks for image level classification, but there are other things that we might want to do. We have talked about entangled decision trees and forests, and of course you can have entangled jungles if you want to, though we haven't done that yet. And for the specific application of segmentation, semantic segmentation, we explored soft connectivity features and then a small modification of a surrogate training energy. And we get state-of-the-art results which compare favorably compared to CRF-based methods. And we have, I spent a lot of work validating this on many, many different databases of very different images. Sometimes we have RGB only, sometimes depth only, sometimes depth and RGB, sometimes we have video, sometimes it's CT, all sorts of things. And it seems to be a generic algorithm that works okay in most cases. So I'll leave you with this slide as before, which is an advertising for us always trying to hire bright people So please do go to these pages. We have internship programs which are now being opened up also to undergrads. So not only for graduates, but to undergrads as well. And so if you're interested or you know people who might be interested, please ask them to go to this webpage or send me an email and I can help them. So I conclude slightly ahead of time.